So before we begin, I would like to acknowledge and pay respect to traditional owners of the land on which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney is built. I also would like to pay my respect to the elders, both past and present. Welcome to the Sydney Nano Distinguished Lectures, the last one actually for 2019. Today we welcome Professor Srikanth from the University of South Florida. He is one of 4 2019 distinguished lecturers of the IEEE Magnetic Society. He's on an academic tour of Australia. So I don't know, the first one was Newcastle, right? Yeah. That was yesterday, and he's going to Melbourne after this. So it's a very busy schedule. Thank you very much for coming here and give us this opportunity to hear from you. He is a professor of physics. He's a professor of physics, and he received PhD in experimental condensed matter from the Indian Institute of Science. He joined the University of South Florida in 2000, and he's the founding director of Functional Materials Laboratory. Today he will be talking about tuning magnetic anisotropy in nanostructures for biomedical application, and I'm personally very interested to know about the biomedical side of it. So his research application spans from magnetic nanoparticles in nanomedicine and radio frequency devices, microwave materials, and complex oxide with competing magnetic phases. Without further ado, he's also actually a Fulbright awardee. So he will be spending times in Singapore at NTU University next year. And that would be a good opportunity for us to collaborate. If you find any field that actually resonate with you, that would be a very good opportunity because that's just 8 hours away. And without any further ado, I welcome you to start your talk. Please welcome him to the podium. Thank you.
Thank you very much, Neil. Perfect, yeah. It's a pleasure to be here in Sydney, one of the most famous cities in the world, and I've been here all of 2 days now. But this morning I was in Newcastle yesterday, and today when I come here, the first thing that hits me when I open the hotel door was this wonderful smoke. So it's amazing to me. I've never seen experienced such a be close to bushfires like this. So it's fantastic. All right, so I would like to thank Professor Gupta and Dr. Gallagher for inviting me. I'm one of the lecturers for the IEEE Magnetic Society, and believe it or not, this is my 78th talk for this calendar year since we started in January. So sometimes it's a blur where I am and what I'm speaking about. So I'm here to tell you a story, the story of magnetic anisotropy. I'm originally from India, as you can probably tell, and we have these mantras. Om is a mantra. So today's mantra is going to be magnetic anisotropy. So hopefully by the end of the talk, as we leave the room, some of you will be chanting along with me anisotropy, because this is a very fundamental parameter in most magnetic materials. And it's also something that can be tuned. And the idea is to tune and engineer the anisotropy to improve the properties of magnetic nanostructures for biomedical applications. And specifically, I'm going to focus on cancer therapy. Yes, using magnetic nanoparticles to kill cancer cells. So that will be the main focus of this presentation. I would like to acknowledge various agencies that have funded my work, and most recently, as Amit mentioned, I'm a Fulbright visiting professor at Nanyang Technological University. I'm supposed to spend 6 months. I've spent it over 2 years. So I'm here for this month and then 2 months next summer, 2020, and also in 2021. All right, so especially I would like to thank the IEEE Magnetic Society for sponsoring my visit, my travel around to give these lectures. I would like to say a few words about the IEEE Magnetic Society. Please don't bother reading the vision statement there. You can go to the website and get the information, but I would like to point out a couple of things. This has the brand, it's IEEE branded, of course, and it's one of the larger societies, Magnetic Society, and there are many programs. If you become a member of the society, you can take advantage of a lot of programs. For example, you get discounted registration fees for some of the biggest magnetism conferences. 2 of them are MMM, which is held in the United States every year, and the Intermag, which is basically held globally. And I think there was one in Singapore last year. So students in the audience, if you become a member, if you're doing anything related to magnetism, or related research, like ferroelectrics, multiferroids, for example, you should become a member of the society, because it turns out that the IEEE Magnetic Society holds a summer school on magnetism every year. And this is held all over the world in exotic places. Unfortunately, not too exotic this year, because it was held in Richmond, Virginia, so 100 miles south of Washington, D.C. Interesting town, but not quite exotic. But to give you an idea, last summer, the summer school on magnetism, sponsored by the IEEE Magnetic Society, was held in Quito, Ecuador. I would have loved to go there myself. Okay? You have to be a member of the society, and students that are selected to participate in the summer school, they get full financial support from the IEEE. It's a good deal. All right. So pass the word around to some of your colleagues who might be interested in this. Well, you can see that I've been busy in Sydney over the weekend, and this is a wonderful city. I enjoyed the experience here. Wow, I didn't have some money over here. This is because one of my Australian friends told me your $50 bill is called a pineapple. But I thought, let me show some strawberries and raspberries and blueberries there as well. So the whole idea is to have this, to make sure that this trip is fruitful for me, this lecture too. All right, so I would like to also take this opportunity to tell you where I'm from. I'm from the city of Tampa. And Tampa is on the Gulf Coast of Florida. That's Florida for you, there's Tampa right there. And we have some of the world's best beaches. I say this with hesitation because I was in Bondi. All right? But indeed, it's one of the best beaches in the country, in the United States. And this is not just me plugging my city. It turns out that there's a magazine that ranks the best beaches in the United States, and Clearwater Beach. Clearwater is a suburb of Tampa, part of Tampa Bay, and that's always number one. Okay? In addition to nice beaches in Florida, we also have major, large universities, research universities, and I'm from one of them. You have heard of University of Florida in Gainesville, which is our flagship university. Florida State University in Tallahassee, where all the big magnets are. That's where our magnet lab is. And I'm at the University of South Florida, so in Tampa, and we are one of the largest publicly funded universities in the country. We've got about 47,000 students, 35,000 on the Tampa campus, and the rest in the branch campuses. I am from the physics department, and it turns out that in my department, we offer a PhD in applied physics. And this is the only one of its kind in the state of Florida. The other big universities, they don't have an applied physics program. So if you want to live near the world's best beach and get a degree in applied physics, we are the only choice. So we would love to have graduate students from Australia, so please pass the word around.
What is it about the beach? Just in one sentence. We're going to be a bit sensitive. That makes it a good beach.
White sand, white, really fine sand. Nanoparticles. Yeah, this is the Nano Institute. We've got nano sand there, nano grains of sand. It's one of the finest sand that you'll ever see on a beach. Beautiful.
Because every time I go to Florida, I go into the
Yeah, but you know, it turns out that shark attacks are not as many as you think. I think that it's a lot easier to get bitten by an alligator, so than a shark attack. Okay. All right. So let me again thank my entire group here for the work we've been doing. And we work on magnetic materials in general. We have several focus areas. Most recently, we're working on spin caloritronics, which is basically generating pure spin currents and manipulating using thermal gradients and measuring the spin Seebeck effect. But that's not the topic of this talk. Today, I'm going to focus on magnetic nanostructures as applied to nanomedicine. These are some of my current students. The ones in green are the ones that contributed to this work. You can see that the first student, Dr. Zore Nimate, this is a PhD work that I'm going to present mostly. Most of her work is being presented today. And she was the one that did a lot of work on nanoparticles and looked at hyperthermia for cancer. As in many magnetic measurements groups or magnetic materials labs, we do a variety of experiments to characterize the materials all the way from DC magnetic properties to high frequency susceptibility. I am going to focus on two experiments today, specifically for this topic. One of them is radio frequency transverse susceptibility that we developed to measure, you guessed it, anisotropy very precisely. That's going to be a theme, as I said. I'm going to tell you how we can measure magnetic anisotropy very precisely, effective anisotropy. That's one experiment we'll talk about. The second experiment is this SAR for hyperthermia. Of course, don't get worried. This is nothing to do with the SAR that you constantly think of. This is a figure of merit, it's specific absorption rate, SAR. And that's the way we evaluate the heating efficiency of magnetic nanoparticles, because eventually they're going to locally heat using nanoparticles, locally heat the cancerous cells and kill them. Okay? That's why it's hyperthermia. So I'm going to tell you how we do this experimentally, how do you measure the efficiency, heating efficiency of cancer cells. So that's the second experiment. Okay, so the outline of my talk is that first I will, note that my students, first I will introduce magnetic anisotropy. I'm assuming this is an outreach talk, so it'll be a broad, basically I'm going to tell you all about how to measure this and how to define these things. Magnetic anisotropy, and the main part of the talk is to use these anisotropic nanoparticles for biomedical applications. How many of you have heard of this TV show, American TV show, Dancing with the Stars? Okay, quite a few. I'm impressed. In your castle, there are hardly like 2 people lifting their hands. All right, so, well, today I'm going to tell you about Dancing with the Stars, on the fun. Okay? So the idea here is to manipulate the surface anisotropy of nanoparticles and thus try to see if you can improve the SAR, or the heating efficiency for cancer therapy. Okay, so that's what I want to do. All right, so what is magnetic anisotropy? Well, if you want to talk about magnetism, you have to start from quantum mechanics, right? Because it's rooted in quantum mechanics. Well, we don't want to go there, so it does take forever, all day. So let's start somewhere. I'm going to take a magnetization vector, magnetic moment. Okay, think of an arrow, the ferromagnetic moment of a magnetic material, and then apply an external field to this. And let's see what happens. Okay? I'm a physicist, like Professor Nicholson here, so I need to show at least one equation. So this is my equation slide. It's a very simple equation. It tells you that when you apply an external field to your magnetic moment, your magnetization, and then it's now competing. They're competing energy scales. One is the external energy field, the magnetic energy of the external field. The other one is the internal energy of the magnetic energy itself, of the material. Okay? So you can write down a simple equation here. The total magnetic energy is now comprised of 2 parts. The Zeeman energy is due to the external field, right? So when you have a large field, you saturate the moment that dominates. Okay? But as you reduce the external field, the magnetization vector is now trying to compete, trying to be pulled by these 2 energy scales, and it finds a position of equilibrium. Okay? And this internal energy can be represented by the magnetic anisotropy energy. It could be magnetocrystalline anisotropy, it could be shape, other contributions to the anisotropy, but that's the fundamental energy scale here, magnetic energy. So it's as important as that. If you're able to manipulate anisotropy, you can actually change the shape of the hysteresis loop. That's the idea. In fact, you can minimize this equation, and that pretty much explains the shape of your magnetization curve. That's towards saturation and then hysteresis, of course. Right? So you can get hard magnets, soft magnets, you can have easy directions for magnetization. The shape depends on the competing energy scales that I just showed you in a very simple manner. Okay? Now this is important because today I'm going to tell you that we need to manipulate the shape of the hysteresis loops for improving SAR, or the heating efficiency of magnetic nanoparticles generated dissipation. This is all we're going to do. Okay, so we can take other kinds of symmetries. For example, we can handle cubic symmetry, no problem, when it comes to taking the magnetocrystalline anisotropy. When it comes to nanoparticles, you have to think about many other effects that might contribute to the effective anisotropy. Let's start from the left here, surface. Okay. All right. So, how many of you work with nanomaterials of any kind? Not necessarily magnetic. Some of you. Congratulations, we're all surface scientists. As you know, nanoparticles are all about surface atoms. Pretty much all the physical properties are governed by the surface atoms, right? So by the fact that you can engineer or manipulate the surface structure, surface atoms, rearrange them, you can have a handle on governing the physical property, controlling the physical property. In this case, magnetism. So that's one way we can do this. We can try to change the shapes. The surface anisotropy, for example, can play a major role in influencing the magnetic properties or the magnetization curves. The second is shape. Shape is quite obvious. You can make nanorods or nanowires. You have a preferred direction for magnetization already there, right? Which is the longitudinal direction. So you can use that effectively for inducing the specific ways to magnetize these particles. And then strain is important. If you take 2 materials and form an interface, then basically the substrate or one of the materials can influence the magnetization purely due to the interfacial strain. Okay, so this can be used to control change the direction of the magnetization. Configuration, I'll come to this later on. I'm going to show you that we can actually make nanoparticle clusters, where we can actually have different shapes, hybrid structures, and we can geometrically change the shapes and thus the configuration, and use that as a handle for changing the effective anisotropy. Last but not the least, this exchange coupling. This is very important for the spintronics community. Almost every spintronic device that you can think of, MRAMs, of course, magnetic random access memories, they're based on this antiferromagnet interface. What happens if you put an antiferromagnet and ferromagnet together at the interface, because of the difference in the anisotropy, the spins of the interface get pinned. And basically, that can be used for changing the shape of the hysteresis loop, like changing the coercivity, and also shift the whole loop. This is called exchange bias. Okay, by applying magnetic field, you actually shift the whole loop, hysteresis loop, and this is behind the so-called spin valves, which are basic elements for spintronic devices. It goes to the MRAMs, for example. So something which is exchange bias, which is so important for the spintronics community, today I'm going to tell you that it's equally important for the nanomedicine community. In fact, we're going to use the exchange coupling in hybrid nanoparticles, or shell nanoparticles, ferromagnetic, antiferromagnetic nanoparticles, and use this to effectively change the shape of the hysteresis loop and control the other properties. Okay? All right, so I keep talking about anisotropic nanoparticles. It turns out that magnetic nanoparticles, anisotropic magnetic nanoparticles are everywhere, omnipresent. Okay, and to illustrate this, I'm going to show you 3 TEM images. Same material, these are iron oxide nanoparticles, okay, ferrites, iron oxide, Fe3O4, magnetite. But the source of where these nanoparticles come from is what makes this series of TEM images interesting. The one on the left, can someone tell me what this might be? These are iron oxide Fe3O4 nanoparticles that are chained up, short chains using dipolar interactions. Turns out that these are bacteria. There's a bacteria, these are magnetosomes, magnetotactic bacteria that produce these iron oxide Fe3O4 nanocrystals, chain them up like this, and they're doing this exactly for the same reason that the Chinese did when they discovered the first magnetic material, which is lodestone magnetite, okay, Fe3O4. So when the Chinese discovered it, they saw that it responded to the Earth's field, and they made, oh cool, we can make a compass out of this for navigation. So these bacteria are making tiny compasses by chaining up these nanoparticles for navigation towards a source of food. That's what they do. All right, but there's built-in anisotropy. That's what I want to focus on. These are short chains, a couple nanoparticles. The second example in the middle is out of this world, literally speaking. Turns out that these are the same magnetite nanoparticles that are found in a chunk of meteorite, alum meteorite, from Mars that crashed into the Arizona desert. Okay? So, well, you've got nanoparticles in life forms, nanoparticles in rocks from Mars. Let's not put them together. That's not my job to convince you that there's life on Mars. But I just want to point out that you get these faceted anisotropic nanoparticles already present in some of these, rocks, for example. Okay? You can see how the faceted surfaces are. You can actually find out what the surface terminations in the topography of this, and it's pretty interesting in itself. By the way, those of you that are interested in the history of nanomagnetism, started in the 1930s, turns out that the people that started looking at the physics of nanomagnetism, nanoparticles, they were not physicists, they were not chemists or engineers. They were geologists. So there were actually people studying magnetism in rocks. They were the first. The geologists were the first that started looking into nanomagnetism. So today, if you walk around the University of Sydney, you spot a geologist, please go and thank them for opening up this nice, interesting area, which has a lot of technological applications now. The third example, you can see that these are ferrites, variation of iron oxides, and they're also faceted, they're also anisotropic. These are man-made, these are produced in large scale by a colleague of mine, a collaborator of mine at Carnegie Mellon University in Pittsburgh. Mike McHenry is very well known in the field of ferrites. And so you can actually produce in large quantities, very similar to the one in the middle, as you can see, faceted nanoparticles. So my point here is that anisotropic nanoparticles are there in abundance. So let's put them to good use, especially for biomedical applications. But before we start talking about biomedical applications, I also wanted to tell you how to measure the anisotropy. Remember the first experiment that I said I'll introduce? This is our signature experiment for my group. So I got to talk about this. Okay? So we made this a very effective way of measuring anisotropy. We do this by a resonant technique. Okay? Here's a schematic of the experiment. So basically, it's nothing but a tank circuit. It's an LC tank circuit. And it's connected to a tunnel diode. Those of you, especially the younger members, the students in the audience, if you remember your AC circuits and the tunnel diode characteristics, you know that there's a negative resistance region, right? There's a region where you bias the tunnel diode, the current goes down, then goes up. So if you bias the tunnel diode in the negative resistance region, it acts as a power source for this tank circuit LC, so it sustains the oscillation. So it can make very stable, self-resonant oscillator. That's what we did. We use this for our experiments. So the sample goes into the inductive coil, as you can see, and then the whole circuit goes inside a superconducting magnet with a solenoidal field that can produce a DC magnetic field. So we can change the external temperature, DC field, and temperature. We put this in what is called a PPMS. I'm sure you have to bring it up on campus here. This is a quantum design fabricated instrument for the superconducting magnet for doing physical property measurements. So we've adapted this and put it inside a PPMS to actually do these resonant experiments, change the external DC field and temperature. Okay? The transverse configuration is because the DC field is perpendicular to the small amplitude RF field on the center. Let's see this transverse cross field geometry. By the way, the cross field geometry is not uncommon. People doing ferromagnetic resonance, FMR, or people doing NMR, nuclear magnetic resonance, you depend on these perpendicular fields, DC field and an RF field perpendicular. That's precisely the same reason why we use this. All we do is put in a frequency counter and measure the shift in the resonance frequency of the circuit. And from that, we can extract what is known as transverse susceptibility. I'll tell you why we do this transverse susceptibility in the next slide, okay? Why we do it this way instead of conventional susceptibility. But first of all, let me tell you something about the sensitivity. As you can see, we can put in a frequency counter, a cheap frequency counter will do, and you can detect shifts of the order of a few hertz in an overall resonance of 25 megahertz. You do the math, you can get parts per million resolution. You can actually look at any fine phase transitions, whether it's magnetic, driven by a magnetic field, or by temperature. So that's the sensitivity. You get very high sensitivity, the high frequency resonant technique. So you can actually pick up switching changes in switching dynamics or change in anisotropy or anything like that very precisely. So that gives us the sensitivity. All right, so now why transverse? Why do it crossed field? Why do it this way? Turns out that we were motivated by a very old paper by a theoretical physicist from Israel, Amit Maharoni, back in 1957. He published this paper in the Bulletin of Israeli Physical Society. It was one of the most well-kept secrets because we couldn't access this, and this is actual result. So what it did was it took a single domain magnetic particle. Single domain particle, it's a simple Stoner-Wolfart particle, T equals 0 calculation, and he showed that you can actually calculate analytically the conventional parallel susceptibility, which is nothing but taking the first derivative of your MH2, right? So that's what it is. And then he also showed that you can also take the transverse component, which is the projection of the magnetization in the perpendicular direction. So if you look at it, it's a tensor. Okay, so you're looking at the component. So he said that if you plot these two, and there's you go from positive high field to low field, so it's positive, and then you cross the field from saturation, you cross the field, change the polarity. This is with respect to the reduced field, and of course the relevant field here is the anisotropic important field for the magnets. Okay? So when you look at this, the conventional parallel susceptibility, you see that after you switch, you have this singular peak. Remember that it's taking a derivative, right? So any change in slope is going to be a peak, sharp change in slope. So that's what it is. It's a singular point detection. Okay? And you see that that's your switching peak. But then he pointed out that if you look at the transverse component, in addition to the switching peak here, you also get these two peaks symmetrically located. It turns out that they are located at the anisotropy field. So he gave a hint as to how to look at anisotropy field in a very precise way to set up this experiment. Okay? And that's what we did. If you look at our geometry, we actually set up to measure, to couple to the transverse component of the susceptibility with this geometry. And so we should be able to see these peaks predicted by Aroni back in the 1950s. And we did. That's why I'm doing these talks, showing the importance of this technique. Yeah, we've been seeing these peaks for more than 15 years now. We can measure the anisotropy field in any kind of magnetic material, whether it's a thin film, a single crystal, bulk, nanoparticles, you name it, with a high degree of sensitivity. That's what gives us this precision for looking at effective anisotropy. So these are from manganite films. They are a class of complex oxides and well studied. The peaks are sharp because these are thin films. The directions are well defined, the magnetization directions. If you take nanoparticle assemblies, we can do even better because remember, we do this experiment in a superconducting magnet, so we can actually follow the entire dynamics, magnetization dynamics, as a function of temperature and field across these superferromagnetic blocking transitions. So what happens is that these nanoparticles, they're tiny, right? So essentially at high temperature, room temperature, for example, if you take these 10 nanometer particles, magnetic particles, they behave like paramagnets simply because the thermal energy, kBT, is higher than the intrinsic magnetic energy. So they are fluctuating, but each one of them is a super spin, so they're super paramagnets. So you can actually see the Curie tail, 1/3 dependence, okay, at high temperature. And then as you cool it down, as you lower the temperature, basically at some point the internal energy exceeds the thermal energy, and so they freeze in random directions, like a spin glass. So see a spin glass like that. This is known as the blocking transition, and we see that. We can actually see that. We can monitor how this fields, the anisotropy fields and switching fields, how they change as you go across this transition. Just to show you how we can do this. Okay, so I told you anisotropic nanoparticles are exciting. I've also shown you a way to measure magnetic anisotropy very precisely. Now let's see what we can do, apply these particles, use them for biomedical applications. As you know, some physicists know that we love breaking time reversal symmetry, right? So I'm going to switch to the other side as I change the topic towards biomedical application of these anisotropic nanoparticles. So here's a slide that shows you roughly what the work is going on, which areas when magnetic nanoparticles are being used for various applications. So quickly, let's start from the left here. Targeted drug delivery. I know that there's some drug conference going on here. Drug delivery, is that a conference workshop that's going on? They will be talking about this, I'm sure. Okay, so basically, magnetic nanoparticles can be used as navigational aids. You can functionalize the surface-attached drug molecules, for example, and these, because they are super paramagnetic, they're magnetic, non-invasively, you can use them in the human body, the bloodstream, and in an external field, magnetic field, non-invasively, you can actually guide them to the area where you want the drug to be released. This is targeted drug delivery or site-specific drug delivery. Now, we don't work in this, but it's an area where a lot of groups are working. Okay. Now, in comparison, the way we take drugs now, we take a pill, swallow a pill, or we take a shot. The drug is coursing through the entire circulatory system. So basically, your whole body is getting affected. That's why we call them side effects, right? So the idea in the future is to only treat the infected area, whether it's cancerous region, or any other kind of infection, by going towards site-specific drug delivery. So it's contained there, and your body is not exposed to it the rest of the body. Okay? So this is the future for drug delivery. An area where we work in, where magnetic particles are already making an effect, is MRI imaging. MRI is a very well-known tool used in all the hospitals. You use it for tissue scans and brain scans, MRI scans. It works based on the principle of nuclear magnetic resonance. Okay? Basically, your water protons, you've got plenty of water in your body, in your cells. So these water protons are set into precession by applying an external field, and then nuclear magnetic moments, very small, right? Very tiny compared to electronic moments. But basically, you set them into precession, and then you apply a high frequency RF signal perpendicular to it. You hit it, and then turn the signal off. When you turn the signal off, the processing moments, they relax. So from the relaxation process, or the relaxation time, there are two time scales here, T1 and T2, I won't go into details. You can get these kind of images. So that's how the conventional MRI images work, based on MR. Now, if you take magnetic nanoparticles and put them in the tissue that you're looking at, the fringing magnetic field, the fringe fields from these magnetic particles, they interfere with the relaxation process. So they speed up or slow down the relaxation time. And when that happens, you can get an enhanced contrast. So this is one thing that has been demonstrated, that adding magnetic particles to the region of scan, you can actually get a better contrast in MRI. There's been a very interesting breakthrough recently, and this is called MPI. It came out of Berkeley from Stephen Connolly's lab group. So basically, a few years back, they showed that instead of imaging the tissue or the cells, here they're imaging the particles themselves. This is magnetic particle imaging. This is a new breakthrough in this field of radiology, or whatever you want to call this, nanomedicine, right? So right now there are a few MPI machines that are out there in the world, but this technology is now basically getting very popular. But the contrast is amazing, as you can see. There's a comparison between MRI and MPI next to each other. This is shown by this company. It's a company called Magnetic Insight in California that basically is promoting this. I'm going to skip cell separation here, and the rest of my talk I'm going to focus on hyperthermia. In other words, can we use these magnetic nanoparticles without any external functionalization or adding any drug molecules? Can we use the particles themselves for therapy, cancer therapy? Can we kill cancer cells with magnetic particles? The answer is yes. We can do that. We can do that by using these particles to generate local heat. And this is called hyperthermia. Okay? Turns out that all we need to do is increase the temperature of the cancer region just a few degrees Celsius above the normal body temperature. So we're talking about a window between 40 degrees and 45 degrees Celsius. Pretty much peak summer temperatures in the city, I would say. Okay? That's all they need to do, expose these cancer cells to this temperature for an extended period of time, cancer cells die. Okay? And that's exactly how we're going to do. We are going to use magnetic nanoparticles to generate this high temperature and sustain it and kill and basically kill cancer cells using that method. Well, I don't need to speak about the necessity of cancer therapy and explore various new technologies for cancer therapies. And this is just a map from 2017. Australia is on the lower side, but then the population is very low, more than 10 times smaller than the United States. So you see that there are densely populated areas where basically cancer is the major threat. And so we need to control this. So when I give this talk, sometimes I have a slide now. When I give this talk, people, of course, as physicists and chemists and engineers, most of us, we think of cancer treatment, our minds tune out because we think, oh, that's the job of the doctors, the medical doctors. That's what they're for, right? No, we can actually contribute to this. This is a highly interdisciplinary area. The physicists, chemists, and biologists as well as engineers can work together towards cancer therapy. There are programs, specifically in the United States, I'm sure in Australia too, that promote this interdisciplinary approach for cancer therapy. Just to make this point, illustrate this point, I'm showing you an article from Physics Today, July 19, 2019, and this article talks about how physical and mathematical models have already led to understanding the process of metastasis. Metastasis is the process by which cancer cells divide and grow and then expand and move to other parts of the body. So we want to understand that because you want to arrest this metastasis, you need to understand it properly. And this is where already physicists are making a contribution here. Okay, so getting back to our goal of using hyperthermia for cancer therapy, this is what we're going to do. We're going to take these magnetic nanoparticles, introduce them to the cancerous region, to the cancer cells, preferably within the cancer cells, have the cancer cells uptake these particles, and then we're going to switch to a large amplitude AC field, AC magnetic field. High frequency, I'm going to tell you all the parameters. We're talking about a few hundred kilohertz, no higher than that. Okay? And as far as the number, it has to be large amplitude also. So it's a high power field and high power AC signal that you need to apply to the nanoparticles, and that will cause them to heat up. I'll tell you the physics of this. So by heating up locally, we can destroy or kill the cancer cells. Remember, the magic window is 40 to 45 degrees Celsius. That's all I need to do. I'm not a biochemist, but it turns out that first of all, you have this protein denaturation, and then eventually the cell membrane. The whole idea is to destroy the cell membrane. And once you destroy the cell membrane, the cancer cells cannot grow. Okay? So that's the goal here. And you do this by heating, in this case, in hyperthermia. So eventually the cell is deactivated or dead, and we call this process apoptosis. Apoptosis, if you may, is a fairly benign way of pushing cancer cells to their own death by heating them, by baking them. Okay, that's what it is. In contrast, the other process is necrosis. Necrosis is a brute force, aggressive way of killing cancer. Do we have examples of necrosis? Sure, we do. That's what we use in hospitals. Very effective. Chemotherapy, radiation therapy, these are all very aggressive in containing cancer, but a lot of collateral damage. Okay? The body's immune system breaks down, and those of you, some of you may have cancer patients in your families or among your friends, you know visibly the kind of changes they go through, experience they go through because of the immune system breaking down. So the idea is that we need to, hypothermia is a more benign way, benign therapy where you don't have these side effects. I've been asked these questions, I'll give an answer right away. People ask me, eventually will hypothermia replace chemotherapy? The answer is no. Chemo is still the most aggressive way of treating cancer. However, as a supplemental technique, hyperthermia in hospitals can help because you can reduce the chemo dosage, you can increase the time between chemo shots, it improves the quality of life of the patients. Okay, so that's the idea. We think that magnetic hyperthermia could be a very good supplemental therapy along with chemo that could actually benefit the patients and improve the process of cancer therapy. Okay, so why is it not in hospitals yet? Sounds great, works, I'll show you it works. Why is it not in hospitals yet? The answer is, in the United States, we have 3 letters, FDA, Food and Drug Administration. There are analogs, I'm sure, in Australia too. For good reason, these agencies they take a lot of time before they approve any new medical technology for clinical trials with human patients. So right now, we don't have approval for clinical trials with human patients in the United States. But our friends across the Atlantic in Europe, especially in Germany, a few years back, they actually approved clinical trials. And this company here, it's called MagForce, it's based in Berlin, in Germany, headquartered there. They've been conducting clinical trials using this technology. They call it the nanothermal therapy. And the statistics they put out they are very impressive. It works, folks. The technique works. Okay. So again, as I said, we're waiting for the approval from the FDA for it to be mainstream, so that we can do clinical trials. Right now, my group, as well as many other groups in the U.S. and around the world, including Australia, Tim St. Pierre from University of Western Australia, Perth is well known in this field of using magnetic particles for hyperthermia. So we all work with rat models. We've shown how tumor shrinks in rats using this technique. Okay? So we're still waiting for this human trials, clinical trials with human patients. But as I said, the company has given us excellent data, so we're in the way on track for hopefully getting this approval soon. So let's get back to some physics. How does this heating take place? How do we heat these nanoparticles? I said you can apply AC magnetic field, right? The reason why I spend a lot of time explaining hysteresis loops and the shapes is because that's the answer. We're going to use hysteresis as a source of heating. Remember that you take any hysteresis loop, the area of the hysteresis loop is dissipation. Dissipation here is in the form of heat. So that's how we want to maximize the area of the hysteresis loop. If you look at this hysteresis, strange looking hysteresis loop here, we want to maximize the area because that gives you the largest dissipation or increases the heat, right? But any of you working with magnetic nanoparticles, if you measure the tiny particles, 20 nanometers or 20 or less, 25 or less nanometers, you will never see a hysteresis loop like this because these are super paramagnetic. There is no hysteresis. There's no coercivity. So please don't get confused by the hysteresis that I'm showing here and the DC hysteresis. That's the DC hysteresis loop, what you measure in a DSM or a squid, in a superconducting magnet. This is the AC hysteresis loop. It's very different. The physics is different. Here, this is think of these magnetic nanoparticles. Each one of them is a ferromagnet. It's a super spin, right, with a large moment. And when you apply an external AC magnetic field at a frequency of a few hundred kilohertz, these moments are trying to follow the high frequency. They cannot. They go out of phase. And the hysteresis loop opens up. So what we are talking about is the AC hysteresis loop to maximize that under applied AC fields. Okay? And now, like any medical technology, any technology, for the matter, we need a figure of merit. And the figure of merit used by the community here is the specific absorption rate, or SAR. It's also called the SLP, specific loss power. One of the same. It's the power dissipated in this process. And just a simple definition of that is that it's the area inside the hysteresis loop multiplied by the frequency. Okay, that's the SAR. And of course, keep in mind that eventually these particles are to be injected inside a human body. So essentially, you want to keep the number of particles down, or obviously they don't want to inject a lot of particles inside the human body.
I'm just curious, how do you get the particles to the right part of the body? So yeah. What's the strategy there?
There's a lot of biochemical functionalization involved. You actually attach ligands, targeted ligands that can target specific cells. So on top, these magnetic particles are just going to be illegal, as we said. Right. And you can use magnetic fields to pull them, but as far as targeting specific cells, you need biochemistry and all of that.
You also know that that's allowing you to get the particles inside the cell.
Exactly. Yeah. I'll show you some examples for you. All right, so we have to optimize this process because we can work with the external conditions, of course, the high frequency source, but we also can manipulate, optimize the particles so that eventually you want to get the highest SAR with the lowest number of particles, right? So that's the ideal scenario. I apologize for the second equation slide. It just tells you, it explains the power dissipation better. Okay, so there's your power dissipation. You can do a linear response theory here if you want. Linear response theory actually works better for anisotropic particles, anisotropic ones, so it works perfectly good. Well, so it's a product of the field amplitude squared multiplied by the frequency. There's a relaxation time involved here because it's a relaxation process. And the relaxation time can be divided into two different types. One is the Brownian relaxation. The whole particle can tumble around, move. So that leads to Brownian relaxation, tau B. And of course, the other one is the magnetic moment rotating, right? So the rotation of moments, that's the needle relaxation. So It's a combination that gives rise to this process that goes into the dissipation. Okay. All right. So now the simplest way to increase the SAR or the heating efficiency is to use particles that have the largest magnetic moments. Okay. You can see there's a simple linear dependence. So you increase the magnetization of the particle, the saturation magnetization of these particles that you're using, your SAR goes up. But it's easier said than done because those of you making nanoparticles, you know that the magnetization goes down compared to the bulk. And this is because the surface is disordered, so really you cannot get bulk magnetization. Okay, with nanoparticles. All right, there's a size dependence for the power, and it turns out that you cannot use particles that are too small or too large. The best particles for this hyperthermia therapy, there's a sweet spot where it is basically close from the single domain to the crossover to the multi-domain. Okay. So that's where it is. So for iron oxide, this size is about 30 to 35 nanometers. That's the ideal size for the hyperthermia therapy. For health reasons, you cannot use particles smaller than 10 nanometers. Period. And that is because if you use particles, because these are being injected into your human body, if you use particles less than 10 nanometers or 5 nanometers, there's a risk of penetrating the blood-brain barrier. So these particles can end up going to the brain. That's the wrong place you want these particles to go. You want these particles to do their job, kill the cancer cells, and go down south to Florida or to southern Australia. Okay? Basically, get flushed out of the system. That's what you want to do. Now, there's a catch right there. So one of the things, I feel that one of the reasons why FDA is dragging its feet for giving approval is because we still don't have a good way of how to take these particles out. Where would they go? So it's an open question. It's like a chicken and egg story. Unless we do clinical trials, how would we know? Right? So basically, it's a process that's very slow, but that's a question that needs to be addressed. How to efficiently extract the particles after the tumor is treated.
The rat models provide an indication of what it might be.
What
the rat model, you mentioned you've done rat models, right?
Yeah, rat models show that, again, rats are completely different from human beings, so it's not, we only have a model. We know that the particles, if you leave them by itself, most of them don't go to the brain, they go to the liver, they go to the kidneys. Safe places, because these organs are meant to be screened, right? They're meant to screen junk from your body.
So you're saying that's what happens in rats?
That's what happens in rats. Especially. Some of them die because of other reasons, but most of the time it goes to the kidney and liver, because we put fluorescent dyes and we watch, we image them as they go around. So we actually confidently say that most of them go to liver and kidney. Okay? We hope that's the same with humans. All right, so about anisotropy, nobody really knows. I mean, for example, can you play around with the shapes and size of these particles, nanoparticles? Can you improve SAR? And this is where we stepped in. Remember, we can measure anisotropy. We were anisotropy jocks, as we think of ourselves. So we thought, why not try to look at anisotropy, the effect of anisotropy of these nanoparticles on the heating efficiency. Okay, so the second experiment that I said, yes.
Anisotropy curve.
Oh, this is just a mark, predicted mark.
Because that is proportional to the anisotropic constant, right?
That's what it is. Yeah, yeah.
Effectivity is the exponential increase.
Yeah.
Not really going up and down.
It's going down because you basically that here it's the power. So the power you have at the top and the bottom. So it's a combined effect. There are two terms. It's a weighted term. Okay. So it's just an ideal approximation. I'll show you better results later on. Okay, so the second experiment I told you that I tell you about is how do we measure the heat efficiency of these particles? How do we measure the hyperthermia potential? So we do that using two different experiments. In my lab at USF in Florida, we use the calorimetric method. Basically, we measure the increase in temperature by putting the thermal sensor. Okay? So here's our AC power source. There's our AC power source. Our particles are in ferrofluids here. They're inside the inductive coil here. We apply. In our case, the power supply has a fixed frequency of 325 kilohertz. Keep that frequency in mind because I'll tell you why we cannot exceed more than a few hundred kilohertz for this technique. Okay, and we can change the AC amplitude to about 100 millitesla, okay, or 1,000 gauss or so. Okay, so what we measure is the SAR, which is the rate at which the temperature increases. So that's why it's called the SAR rate. Right? So basically, we measure how fast the temperature goes up. And remember, we don't need to heat it beyond 45 degrees Celsius. So we need to be able to saturate it right there. So our data looks like this. This is for manganese spherical nanoparticles. We've looked at many different kinds of magnetic oxides. So you can see that it's a function of time. You're plotting the temperature here in Celsius, of course. And you can see that for different, this is a fixed frequency, 325 kilohertz, and these are the applied peak amplitudes. Okay? From looking at it, you see that there's a slope. We need to maximize it so that we can get to this temperature. And then we need to saturate right in that window, the magic window of 40 to 45 degrees Celsius. So just by tweaking the parameters for specific particles, we can find out the ideal condition for getting the saturation right at the temperature. You don't need to overheat it, right? You don't need higher power than necessary. And of course, if you don't apply the right amplitude, you will never heat it. And this saturation is a standard thermoequilibrium process to the environment. Okay? So depending on these curves, we can figure out for these particles of this size, these parameters, frequency and field, are ideal for getting us the right temperature. And then we leave this as a function of time, right? We leave these particles into a patient. The temperature, the therapy has to take place over an hour at a stretch. Okay? So that's how it is done. We make these nanoparticles. I'll show you a lot of them as we go along. And then the same particles that we do the calorimetric method, we ship them to our friends in Spain, in beautiful northern Spain, in Basque Country, Bilbao, where they actually can do the AC magnetometer. They actually built the power supply. The capacitor bank because they have their own large power, right? So actually they made their own capacitor bank and power supply. And in their case, they can actually measure the hysteresis loops at high frequency. So they can do the AC hysteresis loops, and they can get from the area inside the loop, they can get the value of the SAR. Two different experiments throw in the same quantity, figure out like SAR. Okay, here's something I tell the students. Ideally, if you want to publish a paper in a high impact journal these days, in physics, it's Nature Materials, Nature Physics, PRL. Ideally, if you want to prove something, you need two different experiments converging to the same result. Right? So it makes it more convincing for the reviewers to get a paper published fast. That's what we're doing here. Two different experiments, measuring the same quantity SAR, completely different ways. Not just two different experiments, two different labs, two different countries. So the message here is seek out these international collaborations. We need this a lot these days. It's practically a global village these days as far as research is concerned. So seek out those opportunities. You have plenty of them in the United States for hosting international visitors and vice versa. You can always look at this. And I'm on one right now. The Fulbright program is a great way for coming to the United States at all levels, students, postdocs, and higher levels. Okay, I keep saying a few hundred kilohertz and a few hundred more magnetic fields. Why do I keep saying that? Why can't we increase the fields to Tesla fields or crank up the frequency to megahertz and gigahertz? The answer is simple. This is a treatment for humans. We need to work with conditions that the human body can tolerate. We cannot just, these are high power AC fields, right? So AC signals. So we can't afford to just arbitrarily go to values that give the highest value. So it depends on the level that the human body can withstand, especially cancer patients.
What happens?
Oh yeah, so basically you get nerve stimulation. That's the first thing that happens. You get you go to epilepsy or fits or other kinds of abnormalities. So
how much of the body gets exposed?
your body, that depends on the size of where the tumor is and also the size of the system. However, nerve stimulation, if it gets induced to one place, it's an L1 effect. Okay, so let's be very careful about keeping within limits, and that's why in the literature, this is called the Atkinson resolution limit. And in those units, forget about the number. Okay, so it's a product of the field amplitude times the frequency, and we are advised to keep it below that. Think of this as some kind of a pain threshold, right? Now, the best way to explain pain threshold is that in the United States, if we have a patient that goes to ER, emergency room, the first person that meets the patient, we call that person a triage nurse. It's probably the same in Australia. And the first question that the triage nurse, he or she will ask the patient is on a scale of 1 to 10. What is your pain level? And you say 2 or 3, or if you're close to dying, you say 8 or 9. So that's what you mean by this. So we want to make sure that we are below the pain threshold of an average patient. So that's why these values, these external parameters, have to be limited. Hence the type, there's nothing we can do. The only thing we can do now to increase SAR, since there's a limitation on this, is the material itself, the nanoparticles themselves, the nanoparticles themselves. What can we do there in terms of materials to improve the SAR further? Well, as I said, you can look at materials that have a large saturation magnetization because I can give you a higher SAR. So here's the saturation magnetization, the SAR as a function of the magnetization. The bad news is that iron oxide, in this case, is 8203, which is 99, 83 over is almost similar. Okay, it's very low compared to, let's say, iron, one bigger. Iron cobalt alloys even more because the magnetization is higher. However, we cannot put it into the human body. Right? It turns out that we only, again, thanks to those 3 letters FDA, we are stuck with this one material. Only magnetite, iron oxide is approved for biocompatibility, for clinical trials. That's the only material we can use. So we can't think of any exotic, novel magnetic materials that have a large saturation magnetization. It turns out that sometimes in literature I see papers, people making horsehair alloys or something interesting and measuring the hyperthermia. Please don't do that. It's DOA, dead on arrival. We're having trouble convincing the FDA with magnetite, with the biocompatible magnetite, to progress to the next level. So we have to stick with this. Perhaps a tie as far as the material is concerned. So we need to find out ways of improving the SAR, keeping magnetite, the biocompatible magnetite the same. Okay. I already mentioned the size effect. So anisotropy is another issue. That's the only thing you can do. If you only have this one material, let's see what we can do to the material to change its magnetic properties. Yeah, the first thing that comes to mind is let's play around with the surface, let's play around with the shapes. Okay. So this is what we started, and we were one of the first groups to actually start looking into anisotropy, and we make progress, and we're able to convince the community that anisotropy is the key to improve SAR beyond the state of the art and just simple spherical properties. Okay. All right, so, but first, let me show this. But when we saw this curve here, our eyes lit up. Can we fool the cells? Can we fool the cells by making core shell particles with the core being iron, having larger magnetization, and completely encapsulated by magnetite, Fe3O4, which is biocompatible. Right? So basically, have toxic metal inside covered by metal oxide, which is biocompatible, so we can effectively increase the magnetization, and that's the SAR. So we tried that first. So here are our core shell particles. So comparatively, you can see that bulk saturation magnetization of iron oxide is 92. Iron is much bigger. So if you make core shell with the core being iron, shell being iron oxide, you can increase the saturation magnetization, and thus the SAR. We can make beautiful core shell particles. Those are TEM images of assembled core shell nanoparticles with iron core, iron oxide shell. Okay, so let me move on here. So those of you that are interested in chemistry, we do what is called thermal decomposition. Is it okay if I take about 10 minutes? That's fine?
Maybe if you can get into it because we have launched.
Right, yeah.
We can have it.
Sure. Yeah. For those of you that are interested in chemistry, we control the particle size and shapes with simple chemical methods by controlling the time of reaction, temperature of reaction. So we have a beautiful handle of making high quality monodispersed particles. So there's a problem with this because it turns out that when we make metal core oxide shell particles, there's something called the Curtailment effect. The Curtailment effect has been known to metallurgists since the 1950s. By the way, the term metallurgy has disappeared on all the material science. When I was a PhD student, there used to be departments of metallurgy. They no longer exist. Anyway, so here, because of the differential diffusion of the metal ion compared to the oxygen ion, there's an instability. There's a instability at the interface, and because of that, voids open up. This is the Curtailment effect. These voids or holes become bigger and bigger, and finally, the entire iron core disappears. The oxides, the shell gets bigger, and you end up with a hollow particle. So if your goal is to make beautiful hollow nanoparticles, this is the way to go. Unfortunately, it's not good for our hyperthermia because we want to make stable particles, right? Here, the magnetization keeps changing with time. So this is what we found out. We did a sequential study as the core shell becomes completely hollow, and we looked at the dynamic magnetization process. Let me go and show you the results. The proof, I'm going to show them as histograms for comparison, the SAR values. So you can see that the proof of concept worked. As soon as we made the particles, we can show that the core shell particles indeed had a larger SAR because they're the iron core. Okay? But as a function of time, you see that it degrades. So when it becomes completely hollow And that could be days or weeks. You don't have a handle on this time scale. So eventually the SAR goes down, it doesn't heal at all. Okay? So we had to discard this, but we thought the core shell is the way to go. Because remember, in core shell, we can play around the interfacial anisotropy. So around this time, there's a paper that came out of a group in Korea, and they actually made cobalt ferrite, manganese ferrite core shell particles. And one of them is antiferromagnetic, the other one is ferromagnetic. So these both are ferromagnetic, manganese ferrite, ferromagnetic. So it turns out that this is your spin valve. Okay, this is the same that people do in spintronics really do by having this interface. So these are nano spin valves, and they showed that the SAR value is very high because of the exchange and exchange by isotope. So we got pretty interested, but then I took a look at this cobalt. Cobalt is poison. So we can't use the system. This is not going to be approved anytime soon by the FDA. So I challenged my postdocs and students to use a similar strategy and make core shell particles all outside without tetraeder effect. And I'm going to show you that as the last one, and we can discuss the rest afterwards. So we make these FeO, FePO4 particles. FeO is a lesser known phase of oxide. Iron oxide is a Wüstite phase. And guess what? It's antiferromagnetic. So this is the core, and FePO4 is, of course, biocompatible, FDA approved magnetite as the shell. So we made a biocompatible core shell hybrid particle where we showed that it is exchange coupled. You can see the exchange bias shifted the loop, and also shows a very high SAR. So my postdoc came up to me and said, for Harry, by the way, the postdoc's name is Hafsa Khurshid, and we changed her first name from Hafsa to Hermione because she was a wizard in the lab. Okay, and since that time we didn't have a competition. The lab board makes the most exotic, high quality particles. We crown them as Hermione fits a girl and Harry fits a boy. Right? So it's been a tradition now. So Hermione came to me and said, Harry, no, not Harry, this Harry, but aren't you supposed to play with the shapes? I can do that. I said, sure, good luck. She went and came back with different particles of different shapes using the same core shell hybrid. Okay? Which is biocompatible. So these are biocompatible particles. She made spheres, cubes, and these exotic octobars. The surface anisotropy is increasing, as you can see, as you go from left to right. And this is probably going to be one of my last slides, the most important slide of this presentation. You can see very clearly, as you increase the surface anisotropy, go from spheres to cubes to octobars. Just look at that pretty compelling story. Your SAR doubles almost if you increase anisotropy. SAR goes up. Same system, biocompatible, we're not doing anything else. We can show that just like playing with the shapes and sizes, we can increase the SAR. We were the first group to show this, and at that time, nobody really took it seriously. But now, most groups working in hyperthermia, they understand that they need to make high aspect ratio nanoparticles, not just spherical ones. So this was one of the first studies that showed this progression of why anisotropy is important. We also looked at, this is a recent paper in Small, we looked at the bacteria themselves. Remember, they produce these high aspect ratio chain nanoparticles, and sure enough, the SAR was higher compared to the spherical particles. We also made nanorods using a different technique. This is a hydrothermal cell. And again, the best SAR we got in our lab is for these nanorods. So let me wrap up by pointing out that everything that I told you is only half the story. The rest half, we'll talk outside. It turns out that any particle that you make, you need to demonstrate the biocompatibility. It doesn't matter, even if it's magnetic oxide, you still have to do what are called cytotoxicity experiments, which means you feed them to the cells, you go to the cell culture lab, incubate them overnight, 24 hours, 48 hours. You find that the cells have taken up the particles, and then essentially you count how many cells are living, how many are dead. That's how it's done. That's what we value students. It takes a lot of time. Okay, so we do this, and we've shown that some of these particles are indeed very good. And there are other ways of destroying cancer cells. I don't have time to go into that, so let me conclude a little by saying that size does matter. But no, we're not talking about Godzilla. We are talking about nano size, but that nano has been around for a long time. You've heard nano. Nano scale itself has been around. We have to go beyond just the size. I think the key for the future, not just for magnetic nanostructures, but in general for nanotechnology, is to manipulate the surfaces and physics. That's where the new physics, the new discoveries lie in this area. So with that, let me, on behalf of the Functional Materials Lab and also the Magnetic Society, I would like to thank you for your attention. And like you you folks in Australia, some of our best research discussions happen in coffee shops and bars. Thank you very much.
Because we are actually a little bit over time, maybe we end up, if you have only one question, yeah, and then we have the other conversations.
You mentioned the change couple, mean you adding a mean shift bias effect, the shift group. Right. But you mentioned that you change the heat. At the same time, you change the resonant.
Yeah, so let me background. So in terms of the exchange bias, if you do free cooling, there are two ways. One is to shift the loop. The other is you also increase the coercion. Only increase the loop, but depending on the size of the thing, you can also change the coercivity on his oxide. However, remember we're using I'm talking about the AC history as well. So that coercivity change really does not matter. Here it's the shape of the loop. It's the skewness of the loop rather than DC history. Oh yeah, that one is an important point. You have to scan the frequency for that. We can't do it with our experiment right now with our technique, but in principle we are doing it. You might have a possibility of going to a higher, increasing it more. Frequency.
Okay, thank you very much. With that, please join me at